an extraordinary astronomical event is unfolding in the closing months of 2025, one that quietly but profoundly reshapes humanity's understanding of the wider galaxy. On Friday, December 19, 2025, an ancient traveler from another star system will reach its closest point to Earth, offering scientists and skywatchers alike a rare opportunity to study material that formed around a distant sun billions of years ago. This object, known as 3I/Atlas, will pass our planet at a distance of about 170 million miles, or roughly 270 million kilometers, nearly twice the distance between Earth and the Sun, and more than 700 times farther away than the Moon. While this may sound vast on a human scale, in cosmic terms it represents a relatively close flyby, close enough for detailed observation yet safely distant, posing absolutely no danger to Earth or any other planet in the solar system. What makes this moment truly historic is not the distance or the date, but the object itself. 3I/Atlas is only the third confirmed interstellar visitor ever detected passing through our solar system, following the enigmatic Oumuamua in 2017 and the more clearly comet-like 2I/Borisov in 2019. Unlike the countless comets and asteroids that orbit the Sun, bound by its gravity, this object is merely passing through. It does not belong here, and after a brief encounter with our planetary neighborhood, it will vanish forever into the depths of interstellar space. For astronomers, this fleeting visit is akin to a cosmic gift, an unsolicited sample from another planetary system delivered straight to our observational instruments. The story of 3I/Atlas began on July 1, 2025, when it was first detected by the Asteroid Terrestrial Impact Last Alert System, a NASA-funded network of telescopes designed to scan the sky for near-Earth objects. The discovery was made by an Atlas telescope in Rio Hurtado, Chile, a location chosen for its dark skies and strategic vantage point of the southern hemisphere. Initially catalogued as a routine comet, the object quickly drew attention as astronomers began calculating its orbit. Within days, it became clear that something was profoundly unusual. Its trajectory was hyperbolic rather than elliptical, meaning it was traveling far too fast to be gravitationally bound to the Sun. When scientists traced its path backward through time, the conclusion was unavoidable. This comet originated beyond the solar system, traveling for millions or even billions of years before encountering our Sun by chance. This realization earned the object its interstellar designation, the I in 3I/Atlas, and elevated it from a newly discovered comet to a once-in-a-generation scientific opportunity. Interstellar objects are extraordinarily difficult to detect precisely because they move so fast and appear without warning. Unlike periodic comets, which return predictably, interstellar visitors announce themselves only briefly, often when they are already deep within the inner solar system. That astronomers were able to detect 3I/Atlas months before its closest approach is a testament to advances in survey technology and international cooperation in planetary science. Physically, 3I/Atlas is an active comet, meaning it possesses an icy nucleus surrounded by a glowing coma of gas and dust, along with a developing tail that streams away from the Sun under the influence of solar radiation. Observations indicate that when it was first discovered, the comet was traveling at approximately 137,000 miles per hour, or about 221,000 kilometers per hour. As it approached the Sun, gravitational acceleration increased its speed to roughly 153,000 miles per hour, making it one of the fastest natural objects ever observed moving through the inner solar system. Such extreme velocities are a hallmark of interstellar objects, and one of the key clues that distinguish them from native comets. Determining the size of the comet's nucleus has proven more challenging, but data from the Hubble Space Telescope have provided important constraints. Based on brightness measurements and models of how much light is reflected by the surrounding coma, astronomers estimate that the solid core of 3I/Atlas is somewhere between about 1,400 feet and 3.5 miles in diameter. Even at the upper end of this range, the object is tiny on astronomical scales, yet it carries immense scientific value because of its origin. Every grain of dust and molecule of gas released from the comet was forged in an environment shaped by another star, another protoplanetary disk, and another history of planetary formation. Spectroscopic studies have already revealed that the comet's composition is particularly intriguing. Observations from ground-based telescopes and space observatories show that 3I/Atlas is rich in carbon dioxide, with smaller but detectable amounts of water vapor, carbon monoxide, and cyanide. Even more surprising is the unusually high abundance of nickel detected in its gaseous emissions, a feature that challenges existing models of comet chemistry. Nickel is typically associated with rocky material rather than volatile ices, and its presence in the comet's coma suggests that interstellar comets may form under conditions significantly different from those in our own solar system. Each of these chemical signatures provides a clue, helping scientists piece together the physical and chemical environments in which other planetary systems are born. As December 19th approaches, orbital calculations refined by the Jet Propulsion Laboratory and the Minor Planet Center indicate that the comet will pass Earth at a minimum distance of about 1.8 astronomical units, around 6 o'clock Universal Time coordinated. While that distance ensures complete safety, it also means that the comet will remain observable with medium to large-sized telescopes, particularly for professional observatories and dedicated amateur astronomers. Now through mid-December represents the prime window for observation, before the geometry of the comet's trajectory carries it farther away and eventually out of reach of even the most powerful instruments. From the beginning, both NASA and the European Space Agency have emphasized that 3I/Atlas poses no impact risk whatsoever. By planetary defense standards, it does not even come close to Earth, remaining nearly twice as far away as the Sun at its closest approach. Analyses published by NASA scientists and independent researchers alike confirm that the comet will not threaten any planet as it sweeps past the orbits of Mars and Venus and later crosses the region near Jupiter. Its passage is a reminder that not every near-Earth announcement is a cause for alarm. Some are simply opportunities for discovery. Because much of the comet's journey occurs on the far side of the Sun, as seen from Earth, scientists have transformed this limitation into an advantage by orchestrating a solar system-wide observing campaign. Spacecraft positioned around Mars, near Earth, and elsewhere have all been enlisted to study the comet from multiple perspectives, creating a kind of three-dimensional, time-resolved portrait of an interstellar object in motion. NASA's Mars Reconnaissance Orbiter, using its powerful high-rise camera, captured some of the closest images ever taken of 3I/Atlas in early October, when the comet was about 19 million miles from Mars. These images, though faint, provide valuable information about the structure of the coma and the distribution of dust around the nucleus. Other Mars-based assets have contributed as well. The MAVEN orbiter observed ultraviolet emissions from hydrogen gas escaping the comet, shedding light on how solar radiation breaks apart water molecules as the comet warms. Even the Perseverance rover on the Martian surface managed to record a faint detection, demonstrating the sensitivity of modern instruments and the creativity of mission scientists eager to extract every possible data point. Meanwhile, heliophysics missions such as Stereo, SOHO, and the newly launched Punch spacecraft tracked the comet as it passed behind the Sun, monitoring changes in its tail and coma when ground-based telescopes were temporarily blinded by solar glare. Asteroid-focused missions have also joined the effort. Spacecraft like Psyche and Lucy, though designed for entirely different scientific goals, were able to take long-distance images of 3I/Atlas that help refine its orbit and reveal subtle features in its dust tail. On the European side, data from ESA's ExoMars Trace Gas Orbiter, combined with Earth-based observations, improved predictions of the comet's position by an order of magnitude. This achievement is more than a technical success. It serves as a proof of concept for future planetary defense efforts, showing how distributed observations across the solar system can dramatically enhance tracking accuracy. Ultimately, the true significance of 3I/Atlas lies not in its dramatic speed or its exotic chemistry alone, but in what it represents. It is a messenger from